I was looking at the source material for this week, and the notes on the natural fallacy, it honestly triggered a bit of an existential crisis for me.
That is a very heavy way to start a deep dive on compilers. Usually people just get a headache, not an existential crisis.
No, seriously, think about it. We sit here typing these, English-looking words print while...
If class.
Yeah, exactly, into a text file. It feels so human, so logical, but the reality is we're just tricking a flattened rock full of lightning into doing math.
That is a very poetic, if slightly terrifying, way to describe a CPU. But you're right, it feels like magic, but it's really just layers and layers of rigid translation.
And that's our mission today. We are going to ruin the magic trick. We're taking the Class 3 notes, the first 2 chapters of the textbook, and we're going to tear apart exactly how that translation happens.
From the philosophy of language families all the way down to the gritty details of the linker.
Ruining the magic to understand the machine.
I like it. And this is crucial stuff, whether you're a student prepping for the next lecture or a senior dev who's realized they don't actually know what happens when they hit build.
So let's start at the top, the 30,000-foot view. The slides break programming languages into 4 families. And the first one, imperative, it really feels like the grandfather of the bunch.
Absolutely. This is the oldest paradigm. Think C, BASIC, Fortran. It's the do this, then do that style of coding.
It's a recipe, right? Step 1, preheat the oven. Step 2, mix the eggs.
Exactly. And the reason it's the oldest is because it's designed to mimic the hardware. It's tied directly to the von Neumann architecture.
Which is just a fancy way of saying fetching instructions one by one.
Right. The CPU fetches an instruction, it changes something in memory, and then it fetches the next one. Imperative languages are just a human-readable version of that exact cycle.
But then we tried to get a bit more organized with object-oriented programming.
Java, C++, Python.
Yeah, and it sounds like it's really just imperative with, better filing cabinets.
That's a great way to put it. We didn't really change the engine, just the dashboard.
Oh, okay.
Under the hood, it's still all state-changing instructions. But we group the data and the behaviors together. Encapsulation, inheritance, just to manage the complexity. It's about building bigger, more reliable things.
Okay, but then we take a hard left turn into the functional family. This is where my brain usually starts to cramp up. Lisp, Clojure.
You aren't alone. It's a huge paradigm shift. In a pure functional language, the whole concept of a variable as a box that you change the value of, it doesn't really exist.
That just sounds impossible. If I can't say x plus 1, how do I count anything? How do I even make a loop?
You don't. You don't change x. You just create a new value based on x. It's all mathematical. You apply functions to parameters. Input comes in, output goes out. No side effects. No changing state.
And the sources point out a really interesting friction here, because our hardware is von Neumann. It's built to change state functional languages, kind of have to fight the machine they're running on.
That's the von Neumann bottleneck. In a nutshell. Functional code is elegant, it's safe, but running it on a chip that's designed for imperative steps can be, slower. There's a mismatch there.
Which brings us to the 4th family, declarative or logic programming. Prolog is the main example here.
This one is the what not how family. You don't write out the steps. You just give the computer a set of facts and rules, and then you ask it to figure out the solution.
So it's like setting up a crime scene board with all the evidence and connections and then telling the computer, find the killer. You don't tell it where to look.
Precisely. It uses inferencing to do the work.
Okay, so this brings me back to that existential crisis thing. The Class 3 notes call it the natural fallacy. We feel like writing a for loop is the natural way to solve a problem.
But it's not.
It's not natural at all. We've just been conditioned.
We've been Pavloved by the silicon. We think in loops because the chip demands it. If our computers were, quantum processors, a for loop might seem like an insane way to express an idea.
So we aren't bending the machine to our will. We're bending our brains to the machine's architecture.
And that's why we have so many languages. It's a constant balancing act between readability for us, writability for us, and execution speed for the machine. It's always a trade-off.
Okay, so we've picked our language. Let's say we're using C because we need that speed. Now we have to actually run it. This gets us to interpretation versus compilation.
Right. Chapter 1 makes a big deal of this. It's the difference between a live translator and a book translator.
Okay, so interpretation is the live translator at the UN. You speak a sentence, they translate it on the spot.
Exactly. On the fly. It's great for portability. A Python script can run anywhere, but it's sluggish. The computer has to retranslate every line of code every single time it sees it.
Even if it's in a loop that's running a million times.
A million times, yeah. Whereas compilation is translating the entire book before anyone gets to read it.
It takes more work up front, but the result is a finished product.
A finished product that screams. You rewrite the source code entirely into the machine's native language. The CPU doesn't have to think anymore, it just executes.
But the catch is, if I translate the book into German, only German speakers can read it. Compiled code is tied to a specific CPU architecture.
You sacrifice that portability for pure speed. The code you compile for your laptop's Intel chip won't run on your phone's ARM chip.
Now, Chapter 1 asks a great question here that I think a lot of listeners might have. If I'm a data scientist in Python, why should I care about the guts of a C compiler?
It's the difference between being a user and being a master of your tools. Understanding this stuff makes you a better programmer, full stop. You understand the cost of what you're writing.
And debugging, I imagine.
Oh, it's huge for debugging. When you see a linker error, if you don't know what a linker is, you're just lost. If you know the tool chain, you know exactly what kind of problem you're looking for.
Okay, let's get our hands dirty then. The tool chain. Chapter 2 lays this out, and it kind of blew my mind. I always just thought GCC was the compiler.
But it's not one thing.
No. It's like a trench coat with 3 other programs hiding inside.
It's a relay race. When you type GCC, you're kicking off a whole sequence.
Yeah.
And first up is the preprocessor.cpp.
Right, the glorified copy-paste machine.
That's all it is. It looks for lines, starting with hashtag, like hashtag include, and it literally just grabs that file and pastes the text into your code. It doesn't know C, it just knows text.
So my tiny program just became massive before the compiler even looks at it.
Potentially, yeah. Then the baton gets passed to the actual compiler, CC1.
This is the brain of the operation. It translates C into assembly language.
But, and this is a key distinction, assembly isn't binary code yet. It's still text.
Right. It's barely readable text like MOV and ADD and %racks, but you can open it in a text editor and look at it.
So we need another step, the assembler, as...
And this is what takes that assembly text and finally turns it into binary, the ones and zeros, but with holes in it.
Holes, exactly. Think about a function like print. You use it, but you didn't write it. It lives somewhere else, in a system library. The assembler knows you want to call print, but it has no idea where print actually lives in memory. So it just leaves a blank space, a placeholder that says, put print here later.
And that's where the linker comes in, the final runner.
The linker takes your object code, finds the library with print, figures out the real memory address, and fills in all those blanks. It's the glue.
So when I get that awful undefined reference error...
That is the linker screaming at you. It's saying, you promised me this function exists, but I looked everywhere and I can't find it.
That makes so much more sense now. It's not a syntax error, it's a missing puzzle piece.
Exactly.
Okay, we kind of glossed over the brain part, that CC1 compiler step. The slides in Chapter 2 break this down into its own little assembly line. We have to open up that black box.
Let's do it. The example in the book is a simple line of code, height, width plus 56, factor foo.
A classic. So the compiler gets this as just a stream of characters. The first step is the scanner, or lexical analysis.
The scanner is simple. It just groups characters into tokens. It sees HEIGHT and says, that's an identifier. It sees 56 and says, that's an integer. It sees and says, that's a multiplication operator.
So it's identifying the vocabulary, but it doesn't know if the sentence makes any sense?
Not at all. The next step, the parser, handles that. Syntax analysis. This checks the grammar.
It takes those tokens from the scanner and builds the AST, the abstract syntax tree.
Yes, and that tree structure is so important. It turns the flat line of code into a hierarchy. At the top of the tree, for our example, is an assignment node. One branch is height, the other is the whole math expression.
And that's how it knows the order of operations.
It's the grammar police. If you miss a parenthesis, this is where everything explodes.
Okay, so the grammar is correct, but a sentence can be grammatically correct and still be nonsense, like, the cat multiplied by Tuesday.
Exactly. And that's step 3, semantic analysis. This is where it checks the meaning, it looks at the types. Are you trying to add an integer to a string? It uses a symbol table to keep track of what every variable is.
So the parser says the sentence structure is valid, and the semantic analyzer says, yeah, but you can't add 5 to a picture of a dog.
Perfect analogy.
Now, this next part is what I think is the real genius of modern compiler design, the intermediate representation, or IR.
Oh, this is brilliant engineering. Instead of translating that tree directly into, say, Intel machine code, the compiler first translates it to a generic, simplified assembly language. the IR.
But why add an extra step? Why not just go straight to the target?
Modularity. Think about it. Let's say you want to support C, Java, and Python, and you want them all to run on Intel and ARM chips. Without IR, you'd need to write a C to Intel compiler, a C to RM compiler, a Java to Intel.
It's a combinatorial explosion, the M by N problem.
Right. But with IR, you just write a front end for C that outputs IR. Then you write a back end for Intel that reads IR. They meet in the middle. It decouples the language from the hardware.
That is so smart. So if a new chip comes out, you just write one new back end for the IR?
You got it. And this is also where most of the optimization happens. The optimizer looks at the IR and cleans it up before the final step.
Which is code generation. Taking that generic IR and mapping it to the actual specific registers of the machine, like MOVQ with %racks.
And the magic trick is complete. We went all the way from English text to a specific electrical signal on a specific piece of silicon.
That's incredible. It's really a journey of increasing precision.
It is. And it shows you the computer isn't smart. It's just an incredibly fast clerk following a very, very strict checklist.
All right, before we wrap up, we should probably look at the roadmap. The Class 3 slides have some specific deliverables coming up.
Oh yeah, good call. The semester's moving fast.
Yeah.
So for this Friday, January 30th, you have two things. First, read Chapter 3 of the compiler's book.
And Chapter 3 is all about scanning, right? So we're going deep on that very first step we just talked about.
Yep, regular expressions, finite automata. The math behind how a machine learns to find words.
And the second thing for Friday is for the LLM Roundtable. You need to read the article, AI Coding Assistants Are Getting Worse.
Ooh, that sounds spicy.
It does. I'm curious to see what that's about.
It's a super relevant topic. You have to be ready to discuss if these tools are actually helping or just creating more subtle, harder to find bugs.
Which is fitting, given our talk about the natural fallacy. Are we now training ourselves to think like AI?
That's the question. Okay, then looking ahead to Sunday, February 1st. That's when the journal entry for week 2 is due.
And remind us of the format on that one.
It's the 2-1 rule. So a minimum of 2 paragraphs reflecting on the week, and then you have to write one solid quiz question for your peers.
Don't forget that quiz question.
So easy to forget. And just for context, we're moving from week 2 themes, which were estimation and ethics, into week 3, which is all about systems. DRY, orthogonality, debugging.
Systems feels very appropriate after today. We have definitely peeled back the layers of the ultimate system.
We have.
I just want to leave our listeners with that thought about the natural fallacy again. It's really something to chew on.
It completely changes your perspective on coding.
If we just stripped away the last 70 years of history, if we weren't constrained by this von Neumann bottleneck, what would programming even look like?
It's the ultimate what if. If the hardware was fundamentally different, our languages would be different, and the way we think about problems would be different.
We might not be writing loops at all.
Who knows what we'd be writing?
A thought to ponder. All right, read up on scanning for Chapter 3, check out that AI article, and we'll catch you on the next deep dive.
Happy compiling.